Okay, so I think YouTube is running. Welcome to the afternoon session, and the first speaker is Max Wiesner, who's going to tell us about exploring the interior of n=1 field spaces. Thanks, Max.
Workshop here in beautiful Saclay, and I want to talk about some recent work or stuff that I've been working on last year. This is loosely based on a paper that I put out last year around the same time, and some work in progress that maybe gives to some extent my perspective on some of the questions that were discussed actually in the previous discussion session. So since this is work in progress, it's not entirely polished yet, but since this is also a workshop, I thought maybe this is actually a good place to talk about this. So the idea is that I want to explore a little bit the interior of n=1 field spaces, where, as we just heard as we discussed in the discussion session, not much is known when it comes to actually genuine n=1 effects, like how to compute them, what is the structure of the field space in the interior, what is actually the nature of the theories there. So we know that in string theory and also in compactifications, these come often with a number of scalar fields whose vacuum expectation value determine the properties of the effective theory. So the values of the coupling masses of states or value of the IPhT cutoff, you name it. And oftentimes we know, so then all families of the IPhTs are then parameterized by the values of the scalar fields, and so we get a scalar field space where we have different, for example, perturbative descriptions, where we actually have a good understanding of what is this theory, what are the properties of the theories, and the general structure of the field space gives us information about the general properties. For instance, duality frames, we use them a lot in highly supersymmetric cases to infer all our web of dualities, that we know different sectors, different perturbative regimes are actually part of the same moduli space. So what do we know about the structure of M? I mean, it comes oftentimes equipped with some kind of metric which can be computed in perturbative limit of the theory, for example, in perturbative string theory regimes. And for example, in the case of perturbative supersymmetric string theory, which could be one of these perturbative phases where we actually know what to do, one can match this with expectation from gravity and obtain a metric in these perturbative phases. And then if we have enough supersymmetry, actually we sometimes know the entire structure, we know the metric everywhere, because just the structure of just the supersymmetry algebra gives us enough information, and the metric can be evaluated at any point in moduli space. With less supersymmetry, the situation becomes way more difficult, but sometimes we can rely on non-renormalization theorems that allow us to actually interpolate from such a perturbative phase all through the moduli space that I didn't draw here. An example of this is, of course, for the n=2, which we love and which I think we understand very, very good, because at least here the moduli space factorizes into a vector and hypermultiplet sector. And depending on which actual theory we look at, only one vector contains the string coupling, such that the other one is actually tree-level exact, which we know, for example, in type 2 Calabi-Yau compactification, this would be the vector sector, and heterotic on K3 times D2, this would be the hypersector. So, but the question is, what about the more realistic cases in 4D with minimal or no supersymmetry? I'm here a bit more modest, and I want to talk about minimal supersymmetry. But before we go there, let's make some warm-up. What do we actually know in type 2A Calabi-Yau compactification or theories that still have n=2 supersymmetry? Where we draw also, as we discussed or as was discussed in the discussion session, we draw a lot of our intuition from, for example, from the vector multiplet sector of type 2A. So let's first gather some intuition from there, specifically focusing here on type 2A compactification Calabi-Yau treeforms. So we know here that the moduli space factorizes in a hypermultiplet sector, which is spanned by the type 2 dilaton plus axionic partners in the complex structure of the Calabi-Yau X3 plus axionic partner. And the complexified Kähler moduli gives us the vector multiplet sector. Now the n=2 supersymmetry ensures actually the factorization between these, such that we know that the vector multiplet moduli space is tree-level exact, and we can trust the structure that we can derive from a string worldsheet, for example, using mirror symmetry to relate the complexified Kähler moduli space to the complex structure moduli of space of x tilde of the mirror, where we actually have everything classicalizes, and we can just compute our periods in different limits and obtain trustable results. So thanks to the factorization, we can also do this map to the mirror symmetric complex structure moduli space of x tilde, we can actually, this allows us to also describe the small volume regime of the Kähler moduli space of type 2a, which is what we use very often. And we can, for example, infer the singularity structure just from the mirror. So you have here two, in this example, this is just a sketch. We have two moduli. Here we would have a Calabi-Yau phase, and we know that if we go to small volumes, we could get other phases that are not necessarily described by a Calabi-Yau, but by some hybrid phase, by some Landau-Ginzburg phase, or some orbifold phase. So this is the picture that we know and we love. We know how to describe type 2a, the type 2a vector multiplet modular space. And since this is tree-level exact, we can actually also infer what is going on in the small volume limit, where we can still trust our field theory, CFT description, though not necessarily the geometric one. But so, okay, what remains of this picture if we actually go to an n equal to 1, genuine n equal to 1 theory? And what I want to focus here, even though maybe somebody would say, why would I do it and look at F theory? I take the stance, okay, F theory teaches us a lot. It gives us a genuine n equal to 1 theory, so I look on F theory on elliptically fibered Calabi of 4 folds. So some elliptic fiber over some base B3. The scalar field space then is spanned by the complex structure model of X4 and the complexified volumes of devices in B3. And we know that in the large volume regime, if we make the base B3 very large, all the supersymmetry breaking effects that come basically from the non-trivial fibration of the torus over B3 just become very dilute. It's almost a constant fibration. So all the supersymmetry breaking effects are diluted because we can think of VB3 actually that it plays the role of the 4D dilaton. So we get a very weakly coupled theory. And in this limit, the modular space is described by just a factorized. It just factorizes between the complex structure sector and the Kähler sector. And this is what oftentimes is a starting point to actually investigate what is happening in F theory. But so the question is, what happens actually away from the overall large volume limit? So what happens if we do not dilute infinitely much the supersymmetry breaking effects? So what happens, for example, in the small curve limit for some curves in B3, where we in type 2a we somehow on Calabi-Yau threefold we know what is happening thanks to mirror symmetry, and we can somehow infer the structure there. And what about actually the mixing between complex structure and Kähler sector that I think Eric also in one of his questions raised? I don't know where Eric is, but so let's first understand to get an intuition what could be the structure of the Kähler field space in a genuine n equal to 1 theory. So we consider first small volume limits in B3. So naively one might expect a similar pattern as in type 2a. We have shrinking genus 0 curves, which for type 2a fall in these three classes, which are either these flop curves where only a curve shrinks when we shrink, and we can trust actually the classical geometric picture, or we have this gauge enhancement points where a divisor shrinks to a curve, but we have locally enhanced supersymmetry such that we can still trust the classical geometry, or divisor shrinks to a point where we then actually enter an orbifold phase, and we know that our Calabi-Yau phase needs to end eventually. So for F theory on an elliptically fibered Calabi-Yau fourfold, this can at best be true for curves that do not intersect the anti-canonical divisor K bar. So curves that basically do not see the breaking of supersymmetry, or one might call them curves that are actually n equal to true. But of course the interesting case is now not this, because it won't be sensitive to any genuine n equal to 1 breaking effects, n equal to 2 to n equal to 1 breaking effects. But the interesting case is what happens if we shrink a curve C such that it has a non-zero intersection with K bar. Can we trust the classical geometric picture and the Kähler potential derived from it? And therefore, let's focus on these curves. Let's first say, okay, what happens if we intersect this curve once by K bar? Then these are the possible normal bundles, and we take the first case and ask, can the geometric description still be trusted? So we look at one can look at the corrections to the effective action. And we therefore first show that a curve with such a normal bundle, there needs to exist a divisor D whose volume is linear in this modulus, or in the volume of the curve BC. So it necessarily also shrinks in the limit that we shrink this curve. Of course, now this volume, or actually what would be correctly the D3 brane instanton action, receives corrections order alpha prime squared as computed in a series of papers in the 2010s. So these are the kind of corrections which depend on the topological data of the fourfold. So this is just the classical volume which goes to 0 as we shrink the volume. Then we have some correction that are suppressed. If we actually we make the curve small, but we're still at large overall volume. And this would be the relevant correction. So here I have it again. So the question is, of course, if this correction is there, then we see, okay, actually our classical geometric picture breaks down because this correction becomes large and becomes way larger than the classical regime. So does this coefficient vanish for a curve which satisfies this? One can consider, for example, smooth Weierstrass models, which are just over a base that is in itself rational fiber, just to get some intuition. And one can compute this correction and sees that it's precisely proportional to the intersection between the anti-canonical class and C. Hence, it does not vanish in the case this is non-zero or even 1. So it dominates over the classical term. So we cannot trust just the classical field space geometry for such a curve that intersects the K-bar, and actually the corrections take over. As a consistency check, we see if we have a curve that is actually what one might call an n equal to 2 curve, this correction vanishes identically because this is 0. And we can still trust the geometric picture because basically this curve does not see this genuine n equal to 2 to n equal to 1 breaking effects. Another example could be if we intersect this twice and we take this normal bundle, which means that C is actually fibered by a rationally fibered over some base B2, where we have a dual heterotic string theory, which of course was already shown here, but then in the context of the weak gravity conjecture used again and analyzed in detail in this paper. And so what happens here if in the limit of small c at constant overall volume, we again get that all devices, irrespectively of whether they contain C or not, they actually get in the correct limit where we keep this constant. They get a correction which diverges in the limit. And one can now use the duality actually to the heterotic string, exploit this, at least in and show that at least in simple examples, which is what I did here, there's a strong coupling singularity which is reached for a gauge theory on a device at D that is the base, or this is the zero section of this rationally fibered B3. So this guy should vanish at least up to this order in perturbation theory at the singularity. And one sees that all vertical devices with respect to this fibration should have a minimal quantum volume, which one can just write like this, where I want to highlight that there is a slight dependency on the complex structure parameter of X4, which one can actually infer via this duality. So we see that actually that here we reach a strong coupling singularity that you would not have seen from the n equal to 2 parents, or like if you would just apply n equal to 2 logic. And we see a mild mixing between the complex structure parameter of X4 and the base B3. How do I do with time? Okay. So we get a strong coupling singularity at finite distance and a mixing between the complex structure and the Kähler sector, which means that really we should not view this necessarily as two separate sets, but we, as Ilarion said, we have we have just one pack of moduli in the n equal to 1 theory, and dividing these by what comes from complex structure and Kähler sector is a bit arbitrary. So we see that the n equal to 1 theory behaves significantly different from the n equal to 2 counterpart, so we cannot just view it as n equal to 2 plus small corrections, because then we would have not seen this effect. In general, the field space geometry for small genuine n equal to 1 curves is hence not describable by the classical geometry that we just inherit from the Calabi-Yau geometry because of these important corrections. The corrections are big, and the field space does not necessarily factorize anymore. So, but let's say, okay, we go away from this small curve limit, from this very small curve limit, where we would say, okay, if I make a curve that is intersected by the 7 branes, make this very small, then I would also expect the n equal to 1 effects to blow up. Can I still trust the classical field space structure? So can I there still think about this as some factorized, just because somehow there's still some protection from supersymmetry? Or does this really just break down for very small volumes? Or are also corrections important at larger volume, or for example, if I go to large complex structure? And so so one might expect that indeed this mixing between scalar and complex structure is sufficiently suppressed as long as all the divisor volumes are very large. So this would be some picture like this would emerge. So we have here the inverse divisor volume. If this is very large, and here we have the complex structure sector, we can just treat this effectively as the complex structure field space with the scalar potential just coming from the period geometry. Oops, sorry. And this is oftentimes motivated by viewing F-theory via type 2b orientifolds, because in type 2b Calabi-Yau compactification, the complex structure sector is classically exact, so it should not, we can just describe it through this scalar potential, and one could evaluate the periods of X4 reliably to infer the structure of MCS if one wants to work with actual F-theory. And the periods integral, of course, simplify close to boundaries of the complex structure sector, which I would, for instance, put here. This would be, for example, my large complex structure point, or any other of the points that Irene and Thomas classified in detail. So this is typically the setting in which one searches for flux vacuo surface, assuming this factorization. But the question is this picture correct? Therefore, consider a very simple example. It's a very simple example of a Calabi-Yau fourfold. That is an elliptically Calabi-Yau threefold times T2. So our base B3 is just B2 times T2. So F-theory on X4 now leads to a four-dimensional theory with n equal to 2 supersymmetry, but I would not immediately view this as some kind of orientifold. So question, can we already see in this theory what to expect for, this should be a 4, the mixing between complex structure sector and the oval volume modulus? Therefore, in this n equal to 2 thing, we have a factorization between vector and hypermultiplet sector, which is now, the hypermultiplets are now the complex structure moduli of this Calabi-Yau threefold that is upstairs here, and an oval volume B2 plus axiomatic partners. And the scalar moduli of B2 and the moduli of T2 are just in the vector. So this theory is, of course, just dual to type 2a on T2 time, on the same Calabi-Yau threefold. And we can identify the moduli space via a simple map where we identify the complex structure moduli on both sides, and the overall volume modulus of B2 is identified with the 4D dilaton. But we now know that the type 2a hypermultiplet sector receives correction due to D2 brane instantons, and actually which are not necessarily suppressed if we go to certain limits. These D2 brane instantons contribution to the moduli space metric have actually been computed in a series of papers. Here, and I think it started initially with the mirror dual. So we have that the 4D dilaton is the classical one plus a bunch of D2 brane instantons. And in particular, in the large complex structure moduli, in the large complex structure limit, actually the mirror of that, we investigated in this paper in 2019 what is the consequence of this. Or if you actually want to work in type 2a, you should look at this paper by Raphael, Daniel, and Timo. And the effect of this instanton is that they effectively obstruct large complex structure limit at finite value for the dilaton. So we can now break supersymmetry to n equal to 1, for example, through a non-trivial fibration over some P1. And then, of course, at least classically, would expect that the complex structure sector of X3 is part of the oval complex structure sector. And the expectation is also that the corrections that are present already in n equal to 2 should not suddenly disappear if we break to n equal to 1. So this would mean that asymptotic regions in the complex structure sector of X4 also receive corrections at finite volume of the B2, which is now the fiber of B2, due to corrections to what I would now interpret again as the D3 brane instantons on the divisor that is just the fibril divisor, which previously was just the base of the Calabi-Yau. So we get also some kind of corrections that now depend on the complex structure moduli in the limit, and actually you can see in simple smooth Weierstrass models that there is again this C1b3 squared, which tells us, okay, actually if I have a non-trivial fibration for this Calabi-Yau, these guys contribute. So this guy goes actually, because this is just the same as the effect of the D2 instanton, goes to infinity close to the borders or boundaries actually of the complex structure sector of X4, or better to say the subspace of it. And so the consequence is that we can never treat X4 as decoupled from sector unless we are actually at full infinite distance limit. So this, yeah?
This redefinition of the dilaton yourself,
no, it's not necessary. It's already in equal to 2, it's not a holomorphic redefinition.
It's a question of what the right complex structure is.
Yes, exactly. So the consequence is that actually this picture that I drew before is not quite correct. But actually these corrections become relevant unless I take like a double scaling limit, where I first go to large volume and then to large complex structure. So this is one of the upshots. So this is still work in progress, and this is a workshop, so we might discuss. So the conclusion is I wanted to explore the interior of the n equal to 1 field space and see, okay, where do genuine n equal to 1 effects, where do they come from? Can we at least somehow compute them using dualities? And how do they affect the structure of the field space? I focused. I wanted to stress that we can only use the n equal to 1 to intuition if the breaking effects are infinitely diluted. So if we go to large volume, for example, viewing the complex structure sector as embedded in the full moduli space, that this is just possible at infinite volume is very reminiscent of how the vector multiplet sector of type 2b is embedded via the CMAP in the hypermultiplet sector in type 2a. And otherwise, we expect that the n equal to 1 breaking effects are actually important. I explicitly considered F-zero compactifications on fourfolds, where I first showed that the n equal to 1 effects become large if I actually have n equal to 1 curves. And that the mixing between the Kähler structure and complex structure sector and Kähler sector become important away from this large volume limit. And in particular, asymptotic regions in the complex structure sector only describable through the classical geometry in this double scaling limit, which is basically the same that we observed with Fernando and Florent in the n equal to 2 hypermulti sector. But of course, these are still very special cases. So a question is what happens in general n equal to 1 cases, and what can we say there? So this is the work in progress. Thank you very much.
Thank you, Max. Questions?
I'm just trying to sort of get a geometrical picture. When these large corrections appear, so when the curve shrinks, what happens geometrically? Is it
Hold the cube.
Is it some wrapped brain? Is it the curvature becomes large? Or what happens?
In which?
In the case, in this one case that you mentioned just on the previous slide, where the curve shrinks, which intersects the canonical divisor.
Yeah, I mean, you have like the topology states you, or like the topological information tells you that you automatically also shrink an effective divisor. So in F theory, which I don't know how to see this actually directly from type 2.
Yeah, and then what happens?
This is you just get a bunch of corrections. So sorry?
No.
So I was just wondering, do you have any
I
interpretation
would say I don't have a geometric interpretation there. In the same way that if you go to a Landau-Ginzburg phase in type 2a string theory, you don't necessarily have a geometric interpretation.
Well, sometimes there's one in terms of wrapped brains, or you can see something going wrong, like the curvature becomes large or things like that.
I guess that is what is happening, because you saw this effects that are proportional to C3 time wedge J, and if that becomes larger than the classical curvature, then you also this is precisely what is happening.
Yeah. If you ask a question, hold the cube and it will record or something. Yeah.
It's very naive. This dilution in the infinite volume limit, that's usual decoupling between closed and open strings? That is what it's about?
Right, yeah, I would say, at least in F theory, the large volume limit is where basically your vibration becomes infinitely adiabatic, and so hardly changes, so you're supersymmetric.
Right, because the n equal 1 means that you integrate in open string modes, which form n equal 1 multiplets, so you want them to decouple, essentially. Otherwise, I mean, there's no talk about n equal 2, right?
Yes,
I mean, that's the only way I can understand it.
You basically get a triggered vibration, right? Where you would say, okay, the open string sector decouples. Okay. That's interesting.
More questions? Irina.
This is fun.
If you can.
Yeah, so you get that thanks for the talk. You get that the corrections become more important as you go to the boundaries of the complex structure moduli space, unless you have this double limit that you take the volume going to infinity first. But so you explain how it works, but can you repeat, like, what is the intuition? Why the corrections become more important as you go?
So my intuition that comes from the hypermultiplet sector, because if you go in the hypermultiplet sector of type 2a on this, I mean, there you have the two-brain instantons that whose action just becomes smaller and smaller, which is just the C-map of what you saw with Aaron and Thomas, right? That instead of the three brains on cycles that become massless in the large complex structures limit, you now have the two-brain instantons becoming. So actually, there's also a paper by Thomas and Daniel where they analyze this. So these become more and more important. In the same way, you get in the C-dual vector multiplet modular space, you get more and more light states. So they just translate via the CMAP to this kind of corrections to the
Okay, and embodies that this should happen in all boundaries because we always have some massless ones. I see. Yeah. Okay.
So it's as long as you are, I think, at this infinite distance boundary, I don't actually know what happened. But at the conic-fold, we also know that the metric gets corrected thanks to Oguri Wafa, right? Because they calculated this and they say, okay, it's actually there's no singularity anymore because of these trends. And I would expect this to be happening.
There was another question over here and then over there. Yeah.
Okay.
Can I ask a quick question? Or? Yeah, thanks for the very nice talk. I was curious about the correction that you computed to the divisor volume. Say that you have a 77 brain wrapped on that divisor for which you computed the correction. Are you computing the holomorphic correction to the holomorphic gauge coupling, or are you computing the correction to the physical gauge coupling? The reason why physical, then can I just interpret it as F-theory computation of the Kaplanovsky-Louis formula, because it looks awfully similar to that. Basically, yeah.
For Kaplanovsky, if you compare to the heterotic string, for example, and you look at certain devices that are actually the ones that host the D7 brains, then in this paper with Timo and Daniel and Sonju from 2 years ago, we actually matched these to heterotic loop corrections. But in general, I'm not sure if these are, if you don't wrap a 7 brain, then there's no heterotic, then there's no interpretation as in there.
Right, but you can still imagine there, even if you are computing the correction to the D-instant amplitude or you can assume that there is a fiducial D brain or whatever, and then try to compute Kaplanovsky-Louis, right?
But yeah, so at least in the heterotic dual, that's actually one of the things that we used in the paper with Timo and Daniel and Sonju. We actually matched it with the.
That's great.
So because there you see that actually, if you want to match with Kaplanovsky-Louis, there are two contributions. One half of them are already in the classical F-theory geometry. The other one comes in order alpha prime squared. So yes is, I guess, the answer to your question.
Oh, great. Thanks a lot.
Maybe one more quick question.
Hi, thanks for the nice talk. So let's say I have an F-theory realization of a 61, 0 SCFT on a general Riemann surface.
Yes.
In that case, my base obviously is infinite volume. Do I still expect a separation or a factorization of the complex in Kähler moduli?
I mean, you'd say 60 n equal to
61, 0
times T2,
times a general Riemann surface.
Then I would still expect that because the only modulus that is mixing here is the overall volume of the base B2 of your F theory thing, right? And this modulus you don't have if you take a non-compact color.
I see, but the elliptic fibration is no longer it's not locally trivial still, even though I took the base volume to be infinite.
But now you're talking about the elliptic of the Calabi 3 upstairs one.
Sure. Yeah. Okay.
Let me just think.
Oh.
I have to think about it. So I was here now talking about the complex structure and the overall volume, which of course in that example you don't have, but.
Okay. Thanks. Yeah, we can talk more.
Okay. Let's thank Max again for a great talk.